So this problem is asking us to rank the cylinders according to the resistances. So the thing to notice here is that they're telling you that we've got 3 cylindrical copper conductors. So the material is the same. They are giving us the length and the area for each one. So the thing you want to recognize here is that you're calculating resistance. So you're calculating R, and you're going to be using the resistivity. So the resistivity formula, resistance is equal to resistivity times the length, so this length, and then over the area. And then let's just talk about units for a second. So the resistivity, rho, is the units are, ohms times meters. So if I think about resistance, for the units, I'm going to have ohms for resistance, and then for resistivity I'm going to have ohm meters, and then times the length, that's going to be another meter, and then divided by area, it's going to be divided by meters squared, that's the area, right? So my meters cancel with the meters squared and I get the units are correct. So that makes sense. Okay, so now let's work through the resistance for each one. So for A, my resistance for A is going to be R is equal to rho L over A. Right? We're just given regular L and A here, so it just gives us back the formula. But what about B? So for B, we're going to have R is equal to, rho is the same for all of them, and that's because they're all cylindrical copper conductors. So my resistivity is the same for whatever metal I'm using. So if these were different metals, then my rho would be different. But since they're all the same, my rho is the same. So I'm going to have rho, the L is the same again, but now the area is going to be A over 2. So that tells me that for the resistance here, for B, I'm going to have 2 rho L over A. And then for C, I'm going to have R is equal to, same rho. Now I'm going to have 1.5 L, that's the length here. And then my area is going to be A over 2. So then if I calculate what that is, I'm going to get rho times 2 from here times 1.5 times L over A. So 2 times 1.5 is going to be 3 times rho L over A. So it's asking rank from, according to their resistances, greatest first. So I'm going to say that I'm going to have C, and then B, and then A. So let's go on to the next one. Whoops, that's not my next one. That's not my next one. These are out of order, but oh well. Here we go. So this is number 2. And so what's the magnitude and direction of the current in the wire marked with a question mark? Okay, so the way I always start these problems is I'm going to start from the top and at a node. So I've got a node here, right here. This is a node. So I'm going to have current coming in, going down, current coming in, going down, and I'm going to add them. Anytime you have a node, currents add. So in this part, I'm going to have 1 plus 5 amps. So this is going to be 6 amps here. And I'm going to be going down. So 6 amps going down. Now here, right, I'm going to have 2 amps going. So I have 6 coming in, and then I have to have the same number coming out. So the same thing here. I have 1 amp coming in, 5 amps coming in. They add to 6. I have 6 coming in, 2 going out here. So this must be 4. So 6 goes here. I lose 2. So this has got to be 4 amps here. And now I'm going to switch over here and I'm going to look, okay, if I have 4 amps coming in and 3 amps going to the left, then I must have 1 amp going to the right, this way. And so now here I've got 4 amps, and I know this 4 amps is going down here, right? So 6 going down, I lose 2, so I've got 4 going down. So I've got 4 coming in, I've got 1 coming in, so this must be equal to 5 amps here going to the right. So that's my answer, 5 amps to the right. All right, so let's go back and look at this one. And so here we've got a wire. So this is our wire on the left. We have a bigger diameter than on the right. It's talking about current density, right? So let's just, so a wire whose diameter changes. So the diameter, so this looks like, like a hose or something like that, looking at it from the side. They're talking about current density on the left is J1, and the current density on the right is J2. So this is going to be J2 is over here. This is J1. Find an algebraic expression for J2 in terms of J1. Okay, well, we'll do that in a minute. And the diameter of the wire on the left is D, and the diameter here is D over 2. So let's first think about current density. So whenever you have density, that means you're going to have something, so here in this case it's current, over either a length, an area, or a volume. And for this one, we know for current density, it's actually an area. So we think about if I could look at this wire from the side, like if I could look at it from this side with my eyeball here, right, this is my eye, and I'm looking at it this way, I would see an area that looks like this, right? And over here, if I were doing the same thing, looking at it that way, and here's my eyeball, right, I would see an area that looks smaller, kind of like that. And so when I think about current density, I'm thinking about so J is equal to the current, I, divided by the area. And so that area is going to be equal to pi r squared. So I'm going to have this is equal to I over pi r squared. Okay, so so for this side right here, we're gonna say, let's just solve for I. So one of the things I know about this wire is I know the current coming in this side has to be the same as the current going out this side. So that tells me that I can say I on this side is equal to I on this side. So okay, let's write my current in terms of J for the left side. So I'm going to say I is equal to J1 times A1, right? And I over here is going to equal J2 times A. So we'll call this A1 and A2. And just thinking about units for a minute, if I just talk about current density, so current density is something, right, current, divided by area, right? So think about units, I'm going to have that's equal to current, which is amps. It's unfortunate I have A here because I would just write A on the top, but then I've got area is meters squared, right? So so I'm going to have amps over meter squared. So just like always thinking about whenever I talk about density, students really get confused about density. And so you need to know what you're talking about. And so for current, it's always talking about like the current through an area. Okay, so if I want to write down what this current is on the left, I'm going to say I is equal to J1, and then I'm going to have pi r squared. But in this case, my r, I can write it in terms of d, so I'm going to write d over 2, and that's squared, right? So that's my r squared here. And now if I do the same thing over here, I'm going to have I is equal to J2, and I'm going to have pi. And in this case, my diameter is d over 2. So that means I'm going to have d over 2, that's my diameter on the right, but I need the radius, so I'm going to do divide by 2. All right, so d over 2 is my diameter on this side, but then to get the radius, I need to divide by 2 again. So that tells me that my current is going to equal J2 pi, and now that's really like d over 4 squared, right? So, and that's going to equal J2 times pi, and then d squared over 16. So what I can do is my current's the same on both sides, so I can set these two equal to each other. So I can take this and set it equal to this. So I'm going to do that. So I'm going to say J1 pi, and now I'm just going to work through. So my d squared over 4, so d squared over 4, that's equal to J2 pi d squared over 16. So look at all the things I cancel, right? My pi, my d squared, pi d squared, and now I see a 4 on the bottom and a 16 on the bottom, so I can say, well, I've got that's I can factor that, so that's 1 and 4. And so that tells me then that J1 over 4, or J1 over 1 is equal to J2 over 4. And now if I go back up here, it tells me find an algebraic expression for J2 in terms of J1. So I'm just going to write J2, right, is equal to cross multiply. J2 is equal to 4J1. So there we go. All right, I'm going to stop here and then do the next one in a new video just so that these aren't too long.